Hey everyone, and welcome to Dr. Abu RTN Academy channel. Today we are going to discuss part 5 of the biostatistics, which talks about sets and probabilities, and our main focus will be on the probability in this video. In this video, we are going to use the slides, the PDF slides of Debrecen University for the medical students, and the first approach which we have here in this slide is the classical and theoretical. We have more than one approach. One of them, the classical theoretical, we could have practical approach, which are doing practical experiment and getting the result and analyzing it and getting the probability of the result. So we'll start with the classical and theoretical, which is like gambling. You know gambling? Like if you are playing with a deck or paper, so you have this deck which has numbers from 1 to 10, and you have the joker, you have the queen, you have the king. Also you have the dice. We can see here we have dice, we have deck. We can also have this wheel, numbering wheels. So the people who are playing with money and earning money, so the winner will get some prizes or some awards, the winner. So all these are called gambling. So this is theoretical approach because everyone will has an equal chance, and it is known from the beginning that the dice has 6 faces. One face has 1, second face 2, 3, 4, 5, up to 6, and if we throw the dice, every face will have the same chance of the other face. And for the cards, it's 50. For the deck of cards, it's 52 cards, and we have for each shape we have 13 cards under each shape, which we are going to see now in details. So just because some of you are not familiar with the decks and how they are playing it, especially for the people who are not playing or who are not gambling, it's prohibited. I know that in some religions like Islam, it is prohibited to play on money. So here we have 52 deck of cards. So I have a deck of cards consists of 52. All the card decks consist of 52. So we split it into 4 sets, or we can call it 4 suits. So 1 suit, 2nd suit, 3rd suit, and 4th suit. So each suit of them, So here the deck consists of 52 cards. It has 4 suits. Each suit has 13 cards. So 13 plus 13 equals 26. It's 2. The other 2 decks, 13 plus 13 equals 26. 26 plus 26 equals 52. So the total of the 4 decks are 52. So the total number of cards are 52 split into 4. 52 13 plus 13 plus 13 plus 13. Total 52. So 4 13s. So the first suit, which has 13 cards, is the hearts. So we have 13 cards. Each one of them has the heart shape, the symbol of the heart. So start from the ace. So 1 in the card, they are calling it ace. Number 1, there is no number 1. It is only 1 heart, and it's called, or 1 heart, or 1 spade, or 1 diamond, or 1 club, but it's 1 only, and it's called ace. 2, it is written as 2. 3 is written as 3. 4 is written as 4, and so on. So starting from 1 up to from 1, which is ace. That's why they're writing from A to 10. So we have 10 numbers. 1, which is A, 2, 3, 4, 5, up to 10. 10 numbers, 10 cards. Then we have the joker. We have the queen, the king, and we have the queen. So if we can see here, we have 13 cards, hearts, from A to 10. Joker, queen, Joker, king, and queen. And we have another 13 card, the spade. So the heart is the shape of the heart. The diamond, we know the diamond was the shape of diamond. we have the spade and the club. The club is three circles. This circle, another circle, and third circle. So it's called club, okay? So, but the spade is upside down heart with the base, okay? This is a spade, okay? But the club, you can remember the club is three circles. So the last one will be, so the people who find it difficult to memorize the name of the shapes, okay? So in each one of them will have cards from 1 to 10, which you call A to 10, because there is no 1. The 1 is ace. Ace means 1. Okay, and another 13 clubs. Okay, so these are hearts. Here clubs. Okay, these are the clubs. Okay, from A to 10. Joker, king, queen, spade. This is the spade, which is upside down heart, and 13 diamond. Okay. So if I have a dice like this one, okay, and what is the probability of having 1 or 2 or 3? So for 1, the only faces which we can see 1, 2, 3, 4, 5, and 6. Okay, so the possibility of having, or the probability of having the face after we throwing the dice shows 1, it will be 1 over 6. 2 also, it will be 1 over 6. 3, 1 over 6. 4, 1 over 6. So each face, because it is a fair dice probability. If it is fair dice probability, all of them will have the same chance. Okay, the same opportunity, the same probability. So if I say, what is the probability of I throw the dice and I got 1? The probability that it is 1/6. 1 is 1/6. How I get 1/6? What is the characteristics which I'm looking for? I am favoring. I want to achieve 1. I want to get 1. Okay, so what is the chance of getting 1? How many faces has 1? Only 1 face. So I'll say that M small, for example, I'll call it M. The characteristics which I'm looking for, 1. So what is the total number of the faces which I have? Okay, so the total number, I'll call them, for example, N capital 6. So the dice has 6 faces and I'm looking only for 1. So the probability will be M over N. What I'm looking for divided the total number, okay? M divided N equals 1 divided 6. Okay, let us take another example to make it more clearer, okay? What is the possibility or the probability of having an odd number? So what is the odd number here? 1, 3, and 5. Okay, so I have 3 chances. M will be equals 3. So my favorite characteristics, or the characteristic which I'm looking at, is the odd number. So the number of odd numbers here are 3. So M equals 3. What is the total number? Total number is 6. So the probability will be, probability of odd number will be the number of my favorite characteristic, which is 3, divided the total number of characteristics which I have, which is 6, which will be 1/2. Okay. Let us take another example and say, what is the probability of having a number more than 4? Not more than and equal, no, only more than 4. So the probability of having number more than 4 is only 5. It could be only 5 or 6. So M, the favorable characteristics, the required characteristics is 2. The total number N equals 6. So the probability will be 2 over 6 equal 1/3. So let us read what's here in the slide. It says here, in an event can occur, if an event can occur in n ways. So for example, the dice or the event of the dice can occur in how many ways? In 6 ways. We could have the number 1, number 2, number 3, number 4, number 5, or number 6. We cannot have number 7. We cannot have 0, because each phase of the dice has one number, so it could be from 1 to 6. So this is the n number of ways. Okay, it mentioned here it's mutually exclusive. Exclusive means without any complication. It is independent. So for example, if I have a deck of cards, and in this deck of cards I have withdrawn one card. So when I put the card back again and withdraw another card, it will have the same chance of the first card. If I return the card again and I withdraw it again, another card, the new card will have the same chance with the same opportunity. So it's called mutually exclusive. But if I take one card and I did not replace it, I hide it somewhere, so I end up with a deck has the number of cards, instead of 52, they will be reduced to 51. Because I have withdrawn one card of them. So it will be 51 instead of 52. And the number which I have taken, if it is number 3, for example, so 3, instead of having 4 cards, which is having 4 cards, I'll have only 3 cards with number 3. So everything will be changed. So the case which we are talking in this slide is the normal case, which is mutually exclusive. We did not take any card and we did not replace it. No, it is a fair and a fair probability, and every way or every card has equally likely probability to happen. Okay, so here it is mentioned that if an event can occur n times, mutually exclusive means fair or independent. So we are not talking about the special cases, which like we withdrew the card and we did not return it back again. Okay, so mutually we have the first withdrawal and second withdrawal. So the second withdrawal will depend on what the card has been withdrawn in the first one, for example. So this is called non-mutually exclusive. So I have withdrawn a card from the deck, and the first time I have withdrawn a card, and I did not replace it. So in the next withdrawal will be depending on the first card which has been taken in the first time. So this is not our case. This case is called non-mutually. This is called non-mutually exclusive. Okay, but we are talking about here is only the mutually exclusive, the normal cases. I have one withdraw from one deck, that's it. Okay, one dice, and I'm throwing it 1 or 2 or 3 or 4 or 5 times. Every time it has the same chance. Okay, so it should be mutually exclusive, not depending on a previous event happened. Okay, if you remember, we have taken this mutually exclusive in the previous slide when we talk about the sets, and we said we have 2 sets which they are disjoint. There is no overlap between them. They're not depending on each other. There is no overlap in between. So they're called mutually exclusive. We have taken this in the previous video. Okay, so this is the total number. The event can occur in n ways, and this way should have equally likelihood of happening. Like the dice, every phase has the same chance, equal likelihood of happening. Okay, so this is the total number of ways, n, which is the denominator here. The numerator, which is m small, which is the characteristics which possesses what we are looking for. So, and if m of these possesses characteristics, so m number of them are odd number, m number are even number, m are more than 3, more than 4, more than 5, less than 2, whatever characteristics we have. So the m is the favorable characteristics which we are looking for. Okay, so if I have m of them possesses a characteristics, odd number, even number, more than 3, less than 3, joker, queen, king. So this is the m number, and the n is the total number. The probability is m, what I'm looking for, what's I'm favoring, what bosses the characteristics, okay, divided the total number, okay? So the case of more than 4, we said it is only 5 and 6. We have 2, this is M. How many bosses the characteristic? Characteristic here, more than 4. In the last example we have taken, more than 4. If the characteristic more than 4, so we have 5 and 6, so 2. The numbers are 2, okay? Divided the total number of the 6. So 2 divided 6, which is 1 divided 3. Okay, 1 over 3. So in this example, which have been given in this PDF slides, we can pick a card from a deck of 52 ways. So I have 52 cards. I have 52 ways. The total number, okay. So it could be any of the 52 cards. This is the N capital, okay. The total number of ways, the total number of possible ways, okay, is N. The probability of picking heart, okay, and this probability he will call it E, maybe he will call it F, will call it O, will call it Z, will call it K, whatever. So we'll use the same symbol which he has given to us. So we say here probability of the symbol which he has given, which is E, the probability of E, because he called it E. If he called it M, we'll put M. F, we'll call it F. So the probability of E equals M, the number of cards possess this characteristic. What is characteristic? Heart. The characteristic here is heart. Okay? So how many M possess the characteristic heart? Divided the total number N. So how many hearts here? If we look here, we have the deck is split into 4 suits. 4 suits. Each one of them 13 cards. 13 plus 13 plus 13 plus 13 equal 52. So I have heart, 13 hearts. Starting from the ace up to 10, and then the joker, queen, and king. Okay, so I have 13. So the probability will be 13 divided 52, okay, equals 1/4. Okay, 13, which possesses the characteristic of heart. M possesses the characteristics of the heart. 13 divided the total number, which is N, 52. Since 13 card M possesses the characteristic of the heart, the desired characteristics, okay? What we are looking for is heart, okay? So this is the end of this slide. And this is called classical or theoretical approach. Classical or theoretical approach. So we are dealing with it on paper, like the gambling, theoretically, all are by paper. There is no experiment here. So this was the first one, which is classical approach or theoretical approach, okay? And the example of it is the gambling, all this paper and the dices and cards games, okay? Which people are playing on money. But in the next slide, we'll discuss the practical approach. So always the probability is the number of outcomes of the favorables, what we are preferring, the number of outcomes, how many times it will happen, the favorable outcomes, divided by the total number of the possible, okay, of the possible outcomes. Like the dice, all the possible outcomes 6, but the favorable may be 2. If we set the number more than 4, 2. So our favorable more than 4, 2 happens twice. There's 2 chances. Okay, this is the number of favorable, okay, outcomes divided by the total number of possible, not happening, the possible. Okay, so this is always in all the questions, this is the valid definition for the probability. So now we start discussing the probability of the experimental or practical approach. So we have done with the theoretical approach, and now we'll start with the practical or experimental approach. But before we start the experimental and the practical, we need to remind you again about the theoretical probability. I'll give you this formula again. The theoretical probability, which is called also classical probability, could be classical or theoretical. Any of them are the same. So we have classical and theoretical, and also we have experimental and the practical. This is the practical approach, and this is the theoretical approach, okay, or classical approach, okay. The theoretical is based on what I'm aiming for, what is I'm looking for, what's my favorable outcomes, what's my favorable characteristics. So the number of them. For example, the hearts in the deck of cards. The hearts, how many hearts? 13 hearts. So this is the favorable number, 13. So the total number of possible outcomes. What is the total number of the possible number of cards in the deck? 52. So this is the theoretical or classical approach, okay? This experimental or practical approach, if some processes is repeated. So we are talking here about the practical approach, experimental. In experiment or practical, we cannot rely on one data. For example, I made a test and I found the result A. If I repeat this experiment 5 times, maybe I'll find 2 A's and 3 B's, for example. Okay? So it doesn't mean if I limit myself to the first time when I did one experiment only, I found A, I cannot say A is 100%. This is the probability because I did one experiment and the result was A. So it is 100%, no. If I did it twice, maybe one time will be A, one time will be. So A will be 50%, B will be 50%. If I did it 3 times, maybe 1 A and 2 B's. So A will be 33% and B will be 67%. If I did it 5 times and I found 2 A and 3 B's, so A will be 40%. So maybe if I repeated the experiment more and more and more and more, I'll get more accurate results. Okay? So always we have like an approach. So the results are here. When I had some experiment, and if I keep repeating the experiment, by the time I find that the result or the gap between them or the probability, it could be, for example, 0.1, 0.2, 0.3, 0.4, 0.5, and so on. So by repeating the experiment, maybe the gap will be narrowed, and I find the approach of them that they are going, for example, to 0.5. So all of them are tending to reach 0.5. From 0.9 to 0.1, so they will be reducing, and here reducing, and here increasing, and they will be approaching 0.5. So I expect that if I increase the number of experiments to infinity, 100 times, 1 million times, 2 million times, infinity, maybe I reach to the answer at the infinity, which will be very closer to the trend of these results of the experiment. Okay, that's why we have here limits. Limits means that we are trying to limit our answer to a number. It was big variance, big gap between them, big difference, and now we are trying to narrow the gap between them to reach a number. So we call it limiting. This is the limitation problem. This limitation happens if we keep increasing n. So have 1 experiment, 2 experiments, 3 experiments, 4 experiments, up to infinity. If n is going to n approaching infinity, n approaching infinity means n is increasing 1, 2, 3, 4 up to infinity. As far as it's increasing and going toward the infinity, 1 million, 2 million, 100 million, and so on, so we are getting the answer. So m divided n will be the probability. It might be 0.5. It might be something else. But what I'm saying that instead of having variety, we said it's in the range of 0.1 to 0.9, the probability. So it is a big range because probability is greater than or equal to 0, and it is less than or equal to 1. If I say from 0.1 to 0.09, it is big variety, big gap between them. It is unreliable, so everything is here because it is very closer to 0 to 1. So we did not do anything here. But if we keep repeating the experiment, we'll get closer. So if we repeat the experiment 100 times, we'll get more closer to. So if I did once, I get, for example, 0.9. I did twice, 0.7. 100 it became 100 times and took the average. The result became 0.6. I take 1 million and take the average, it will be 0.5. 3 million, it will be 0.499, for example. So I did infinity. There is no infinity, we cannot do, but let us assume it will be 0.49. So the answer is 0.49. We cannot do infinity, we cannot do million, we cannot do thousands of experiments for the same thing, but at least we know the approach, the trend of them, where they are going, and theoretically we can draw the graph and we can expect where they are going to limit or to end. That's why we said limit, okay, limitation, when n tend to going to infinity. So this is the limitation, or this is the probability in this case. So if some process is repeated a large number of times n, so the number of times n, usually when you see this in the slides, he writes here the description and then the notation of it, large number of times n, and if some resulting events with characteristic E, so this is a characteristic E. So E is the symbol of the characteristic. Okay, if you find B, E after that means probability of the characteristic E. That because now you know that the characteristic is called E. Could be B, Z, K, whatever. But here in this example, it's called, or in this slide, it's called E. If some processes repeated for a large number of times, okay, n number of times n, and some resulting event of characteristics E occurs m time, so he did the experiment n time, and the result occurs or happened m times. So n, the total number of times he repeated the experiment, 100 times, 1000 times, 2000 times, and the result occurred m times. So the relative frequency of E is a characteristic. Okay, you remember we just said that E is the characteristic, okay? Is M divided N. The number of occurrences divided the total number he has done the experiment. And we'll see in the next example, it will clear the picture for us. Just for those who doesn't know the coin and the head and tail, before in the old coins, there was one face of the coin which has the head of the queen, and the other one which has the tail. That's why they called it head and tail. Okay, in some other countries they call it the number and the picture, number and photo, because it has one number, 10 euro, $10, 15 one side, and the other side is the photo of the king or the queen. In this example, we will talk about an event which we have a coin which is tossed 10 times. So how many times n? The total number, how many times we tossed it? N equals 10. And the head is recorded 7 times. So M, this is my favorable characteristic, or the thing which I'm preferring, which is I'm looking at, which I'm looking for, okay? The head, I'm looking for the head. Head appeared or recorded 7 times. So M equals 7 times. And the tail 3 times. Okay, but I'm looking here for the head. So the probability of the head, how many times the head appears? The head appears 7 times. It will be 7. And how many times we repeated the test? We repeated the test 10 times. It will be 7 over 10, 0.7 equals 0.7. If I'm looking for the tail, how many times the tail appears? The tail appears 3 times. And the total number of experiments, how many times we have done the experiment, the number of trials, 10 times. So it will be 0.3. Okay? Here even, if you look at the definition of the experimental property is found by repeating an experiment. We have to repeat it. For example, we repeat it 10 times. Maybe if you just toss the coin 1 time, you will get a head. You will say the head is 100%, which is not right. If you repeat twice, the probability will be changed. If you repeat 3 times, 5 times, 10 times, 100 times, it will be changed. Okay? So it is found by repeating an experiment and observing the outcomes. So P of the event could be head, event could be tail, event could be the heart, or it could be diamond, it could be whatever. Okay? So P, the probability of the event, equal the number of times that event, the tail or the head or the heart or diamond or whatever, occurs, the number of times the event occurred divided the total number of the trials. So here in this example, it says that flipping a coin once. I have a coin which has head and tail, and I'm flipping it once. From our head, if I said I have a coin and I flip the coin, I expect that the probability of the head is 50%, probability of the tail is 50%, so 0.5 and 0.5, total is 1. Okay, this is the logical thing, that probably the head will appear, has a chance to appear 50%, the tail has a chance to appear 50%. We have only two faces. If I throw it like the dice, if I throw it, I have the probability 1/6 for each face. Also for the head and tail, for the coin, if I flipped or tossed the coin, I expect that the head has a chance of 50% or 0.5, and the tail has a chance of 0.5, the probability 0.5. But in reality, if I did an experiment and I flipped or tossed the coin, maybe I end up with, I'm looking for the tail, maybe I end up with a head. So the probability of the tail in this case will be 0. From the experiment, I did the first experiment, it came head. I'm looking for tail. I'm looking for the tail. But when I did the experiment, the first experiment, it became head. So the probability of tail, P of tail, equals 0 in this case. If after I did the first experiment, it was a tail, so the probability of tail is 100%, 1. But the logic says that the probability of tail and head should be 0.5. This is the possible number of possible ways. But if I did one experiment, everything changed. The probability of tail became 0, or the other way around, it came 1. But if I repeat it twice, I may end up 1 time tail and 1 time head, so it will be 0.5 and 0.5. If I repeat it 3 times, 4 times, 100 times, so the number will change, keep it changing until we reach the normal probability, the logical probability which we are expecting from the beginning. Okay, so this is the case of head and tail because we have only 2 options, but you might have 2 events, 3 events, 100 events. For example, the deck of cards, you have 52 events, 52 ways. You may end up with 32 here and 20 in the other side, or 40 and 12, and so on. But they will go, at the end of the day, they will approach that, for the heart, the probability of the heart, it will be 1/30. The probability of the diamond will be 1/30, and so on. So if we go through this example, flipping a coin once, the relative frequency of getting a tail is either 0 or 1, because once, you did it once, 1 time. Either it will be head or it will be tail, right? It will be head or tail. It will be head or tail. So if it is head, the tail will be 0 and head will be 1. If it is tail, the head will be 0 and tail will be 1. As opposed, on contrary to our expectation. Our expectation that the probability should be 0.5 for the tail and 0.5 for the head. Okay? As opposed to the probability of 0.5 expected for the tail. But after many flips, the relative frequency of the tail will approach 0.1. So when they started here, 0 trials, or when they started the first trial, we end up with the probability of the relative frequency, it's almost closer to 0. So this means that the head appears. Then when it is repeated, it became 0 up to 0.6, the tail. Then it drops down. After we repeat 500 times, we reach 0.5. Okay? So if we have more number of experiments, more number of practical tests which we have, so our data will be more realistic. We can rely on the data. But if we did it 1 or 2 times or 3 times, it will be less realistic. This along with some other factors which impacting the reliability of the experiment. But here we are talking about the probability. After we already got the data, we have to look at the sample which we have taken. Is it big sample or small sample? The number of repeating the experiment, this is a very, very vital and important factor or parameter which impacting the results and the conclusion which will be drawn from this results. Okay, so if we repeat it, as we can see here, if we took the impression and decided based on the first experiment, we'll say the probability of the tail is 0. But after we repeated 100 times or 50 times, it becomes 0.6. It is not 0, it is not 0.6. If we repeated 200 times, it is 0.55. But if we repeated it for a large number of experiments, we will end up with reach something which is very close to the realistic one or the logical one. Okay, I hope this is clear for the experimental approach as well.